Hi everyone, lesson 4.2 is very exciting. Today we are learning the very important definitions for relations and functions, domain and range. Things that you will be using from now all the way up into grade 12 and beyond. After this lesson, you will be able to define a function, relation, and you will also be able to define what domain and range are. So just the definitions of these words you will know by the end of this lesson. The other thing you'll be able to do is you will be able to distinguish a function from a relation. So everything we're looking at today is a relation, but some of them are also functions, and I'll help you distinguish which is which. And what we will be able to do is state the domain and range of various relations. So I'm going to give you relations, and you will state the domain and range of those relations. Now I'm throwing around a lot of definitions, so let's begin with our first one. A relation is pretty simple. The definition of a relation is when an x value is associated, or let's use the word linked, with a y value as an ordered pair. Okay, so basically they come as a package deal, x, y. Okay, so it's a relationship between x and y. The root word here, relationship, think of like a friendship. X and y are friends, and they're linked together as an ordered pair. They're partnered together as an ordered pair. So the other thing I want to emphasize is that this could be random or in a pattern. And the way I want to demonstrate this is by just giving an example, a graphical example. Okay, so what do I mean by random and what do I mean by a pattern? So for example, if I plot this point, what I've done is I've associated this x and y value together as a partnership. So if I draw like sort of a scatter plot, I am able to associate random x and y values together. I'll just call these all x, y. I could call them x1, y1, but these are all random x, y values. We've already learned a couple of ways to associate x and y values together in a pattern. So, for example, if I gave you this equation, and I asked you to plot all the x, y values that obeyed this equation, you would draw something like this. If that was -4, you would probably plot a whole bunch of x, y values. And in fact, I'm not just writing the dots, it's all of the values in between those dots as well. So as I can see, all of these x, y values are associated together. They're partnered together, but this is in the form of a pattern. Another example we could use is a circle. Okay, so I could say maybe this circle has equation x minus 3 squared plus y squared, because it's obviously on the x-axis, equals 1. So again, this is a pattern of x, y values that are associated together, and all of these things here are relations. Okay, so I could have individual random dots, or I could have patterns of dots where there are more than one associated together in an equation. So we've already sort of summarized the 3 different ways a relation can be represented just by the stuff we've covered so far. So there are 3 ways we can represent a relation, and I'll go with the most obvious one first. The most obvious one is an equation. Okay, and what I mean by that is x and y are linked by the equation. Okay, so for example, we have a line. Okay, this is one example. So y equals, let's say, 2x plus 3. Okay, I can write it like this, or I can write it in standard form if I want. They're both the same. Or how about a circle? Okay, I can see all the xy values on the circle would have to obey the equation for the circle. So the graph of the circle describes all the xy values are related by x squared plus y squared equals 25. We could also have one that's off center. Okay, so the first one's centered at the origin with a radius of 5. The second one is centered at 3, 4 with a radius of 10. Finally, I know you don't know what this is yet, but we're going to learn all about it this unit. We have this thing called a parabola. It looks like a horseshoe or a U. And we know we've already dealt with, let me just give you some numbers here. We've already dealt with ax squared plus bx plus c quite a lot, but we haven't actually associated it with a y value yet. But you can see the idea that if I take an x value and sub it in, I'll get a y value. And these are all the xy values here are linked together by the equation. It is a relation. The second way I can describe a relation is through a graph. Okay, and we can see the xy pairs on the graph. And again, this can be random or it can be in an equation. So we've got ourselves a line, for example, or a circle, for example. Okay, we could have a parabola. But I want us to show, let's put one on here that's a little bit different. Okay, so if I gave you a graph like this, okay, which looks like a staircase, should look like a staircase anyway. That's what I'm trying for here. Oops. Okay, let's pretend this looks like a staircase. You know what? Writing the equation is actually a lot more difficult than just looking at the graph. So I could look at the graph and see that all these xy values are associated together just by looking at the graph visually. Okay, the last way I can represent a relation is very simply through a set of ordered pairs. Okay, we call these sets, okay? And the reason we call them sets, well, they're just called sets. We denote them with an S. And I'm going to give you an example of just a set of ordered pairs. What we notice is when we use sets, we can do something that we can't do in equations and graphs. Well, I guess we could do this with graphs. But I can give you a whole bunch of disjointed random points. So if I want really random points, okay, I can just basically take all my favorite xy values and associate them together in coordinates. Okay, and we can see that if we want to, we can graph these, but we definitely cannot write an equation to plot these. So if I have, 5, 2, 5, 4, 2, 0, -1, -10, You get the idea. Okay, so there's not really necessarily any pattern here. Okay, so we know what a relation is, and we know how to represent a relation in 3 different ways. Now we're getting to a really big definition, which is deceivingly simple. Okay, we're going to do lots of practice though, don't worry. So what is the meaning of domain? A domain is all the x values of a relation. So it's basically just a list of all the x values of a relation. And this is in a pattern or random. So I'm going to show you how to write it down in both scenarios. The range is all the y values of a relation. Again, pattern or random. And we are going to do some examples of that. So let's take a look at this set of ordered pairs, and I want to determine the domain and range for each of the following. So here's what we're going to do. I look at all the x values in this set of ordered pairs, and I just write them down. That's it. My domain here is x equals 1, 3, 5, 7, and 9. That's it. It's just a list of values. Let's take a look at our range. So my range is going to be the list of all my y values. Two, 4, 6, 8, 10. So when I give it to you in a set of ordered pairs, you can just look at it. If I give it to you as a graph, you have to do maybe a little bit more work. You have to look at the coordinates on the grid. So I can see that my x values are -3, -1, 1, 2, and 3. And my y values, or my range values, are, and I always start with the negative numbers, and I go up from negative infinity towards positive infinity. So in this case, y is -2, 0, and I don't write 0 down twice. I don't do that, okay? 0 is there. If it's there, you only need it once. -2, 0, 2, and 4. All right. Domain and range. So if I want to look at this graph, I can see that it's a line, and I know that the line is going to go on forever outside of this field of view. So I always make the assumption that graphs keep doing what they're doing. So what I can see is that this graph actually covers, like if I were to consider all the x values that are covered by this line, well, really, it's all of them. So instead of writing the word all of them, or the phrase all of them, I need something more mathematical, okay? So what we actually do is we say that we say the following. We say x, e, r, and I'm going to explain this. So x is just the same thing. X denotes that it's the domain, but we have these two other things that are important. So the e part means is an element of. So that symbol e represents or replaces the phrase is an element of. And this r stands for the real number system. Real numbers are all the numbers between -infinity and infinity, which I can see that the x value takes on, the domain takes on. And if I want to consider the range, well, same idea. I can see that all the y values are covered on this graph, by this graph. So what I'm going to do is write y, because that denotes the range. Y is an element of real numbers. Now for this graph, this parabola here, again, I'm going to consider that the graph keeps doing what it's doing outside of the field of view. And even though it's doing it really, really, really slowly, what this graph is doing is it's covering negative infinity to infinity again. So the domain of this graph is XER because I know that the X values keep going out and out and out. The Y values, however, have a minimum. I can see that they start at 0 as its minimum and they head up to infinity. Okay, so in this case, what I want to do is have a minimum value for Y, and this is how I denote it. I say 0 is less than or equal to because I can see that the point 0 is actually on the graph. 0 is less than or equal to Y, plus Y is an element of real numbers, meaning that it's not dots, it's all the numbers in between, like the little teeny tiny decimals in between all these values, I can tell are on part of my graph. Okay. So let's take a look at this next graph. What you may or may not be able to see is that there's actually an empty circle here. Okay, so when we go to find the domain and range of this, what I need to recognize is that that point is actually not included on the graph. So in this case, my domain, okay, so I can see that my domain starts at -4, but actually it doesn't include -4, so it's like an open circle at -4, but it includes all the numbers up to positive infinity. So that's denoted by, this arrow going out of the field of view. I know it's going to keep doing what it's doing, so I know all the X values greater than 4 are included. However, not including -4. So I'm not going to write less than or equal to. And guys, I don't have to write is less than infinity. That's not a thing. Okay, so we just leave it the way it is. It's -4 is less than X, XER. And similarly, the range is going to be -1 is less than Y, YER. All right, let's just skip F. I want us to find the domain and range of this equation. Well, what is this? I know this is a circle centered at the origin with radius 7. So if I were to make a little sketch of this, okay, I should be able to see what the domain and range are pretty easily. Well, I know the domain is going to be -7 is less than or equal to X is less than or equal to 7 XER. And my range is going to be exactly the same thing. And that's because if I look at all the X values of this circle, they're from -7 to 7. And if I look at all the Y values, it's also from -7 to 7. We always start from negative infinity and work up to positive infinity. All right, what about a circle with radius 6 centered at -1, 4? Let's draw a little sketch. All right, so if my center is at -1, 4, maybe let's do this. -1, 4. Okay, I know it's going to go out to, if I add 6 units to -1, I know this goes out to 5, and it's going to go down to -7. It's going to go down to -2 on the y-axis, and it's going to go all the way up here to 10. So if I were to draw this circle, which is definitely not going to be perfect, okay, it's going to look something like that. Maybe let's move this up a little bit. All right. What is the domain? Well, the domain goes from -7 all the way up to 5. -7 is less than or equal to x is less than or equal to 5 xer. And similarly, with y, we've got -2 is less than or equal to y, which is less than or equal to 10 YER. I didn't actually need to draw the graph, but I think it's helpful. So -2 all the way up to 10. All right, now it's time for a definition of a function, which is really important. So the definition of a function is very similar to the definition of a relation, but with one really important change. A function is when an x value is linked with one unique y value. Okay, in an ordered pair. How does that differ from what we talked about earlier? Let's do some examples. So let's say I have this line here. And what I can see is that on this line, if I were to take an x value, I don't know, let's say x equals 3 here. And if I were to go up to the line, I would see that that x value would have a particular y value. Let's say y equals 2. And for every x value on my graph that I pick, I only have one unique y value associated with it. That would make this a function. Let's look at something that is not a function. Okay, so something like this, okay, which has no graph as far as I know. This would not be a function because if I picked x equals 3, I would be able to find this y value. I don't know, let's say this is y equals 2. And this y value, I don't know, let's call that y equals 3. And maybe this y value. So I can see that for one x value, I have 3 different y values. For one x value, I have 3 different y values. This is not a function. Okay? However, they're both relations. I'm going to do one more example because this is a common misunderstanding. If I draw this guy, a parabola, and let's say I take this value, or let's say I look at this point right here. Okay, so I've got x equals 2. Okay, and let's say, for instance, that this is this y value is 4. I know that this point here is 2, 4. But if I travel along this way, I can see that I have another point here, and it's going to be symmetrical. I've tried to draw this symmetrically at -2. Okay, and this point is -2, 4. Well, remember that the definition of a function is that the x values have a unique y value, but it doesn't say anything about the y values. So even though I have 2 y values, the same y value with 2 different x values, in this case y equals 4 is associated with -2 and +2, that's okay because that doesn't violate our definition of a function. So yes, this is in fact a function. Okay, so you are allowed to have the same x value with two different y values, but not vice versa. Okay, so just a reminder that all of these things here are relations, but only some of them are functions. So the way I want us to think about this is that in the set of all relations, okay, only a subset of relations are actually functions. Okay, so we have to be able to deduce which of the relations are functions. I'm going to write that down. Okay. So let's look at some relations and determine whether they are also functions. So the first thing I want us to recognize is that these are all relations because they link up x and y values. Now what we're going to do is we're going to look at the x values and see if there are unique values of y or if there are repeated values of y that determine whether or not this is a function. So if I look at A, what this means, you might be wondering what this means. Well, this is another way of writing out the points 112, 223, etc. So I'm associating x values with y values. But we can see at the bottom that we have 667 and 688. So for one x value, we actually have two different y values. So what that means is that this thing is not a function. Okay? But y is allowed to have two different x values. So in this case, we have 667 and 767, and this is okay. So in this case, we know that all x values have only one y value. So yes, this is a function, not a function. When I look at a set of ordered pairs, it's very similar. What I basically have to do is see if there are, for every x value, I have just one y value. So I can see that, yes, this guy here is a function. Because that rule isn't violated. But if I look at the next one, I can see that the x value of 3 is associated with 3, but it's also associated with -2. Okay, so this is not a function. And remember, these are all relations. Okay, but only these two guys are functions here. All right. Now, visually, it's really easy to see whether or not a graph is a function. And the way we can do this visually when I have the graph is by considering a vertical line. So a vertical line helps us to see if one of the x values has more than one y value, which would mean it's not a function. Okay, so if at any point a vertical line intersects the graph at two or more points, more y values, the graph fails the vertical line test, VLT, vertical line test, and is not a function. If it passes the VLT, it is a function. So let's do an example. So, okay. If I draw this vertical line here, I can see that it only intersects my graph once. Let's use a better color that everyone can see. Sure. Okay, so I can see that it intersects my graph only once. And in fact, this is true for any vertical line I try to draw on this graph. And of course, we know that we assume that all of these graphs keep doing what they're doing. So this guy would pass the vertical line test, meaning it is a function. For the second example, we can see, except for, the lines that don't intersect the graph at all, or for one very special line that only intersects the graph at one point, all the other ones intersect at 2 points. And in fact, I only need one failure to make this not a function. Okay, same deal here. Even though this passes, as soon as I get into this section, I intersect this graph 3 times. It fails the vertical line test and is not a function. All right, we can see that this guy is not a function. And this is just a bunch of dots, right? So it's not including the, the in-between parts. This one looks like it might fail the VLT, but actually it passes. If I look at all the points and all the lines I can draw, this actually passes a vertical line test because it doesn't intersect more than once. It's a function. Now, I could give you equations, and you would have to deduce sort of whether it's a function or not just by knowing what the relation is. This is a circle, and all circles fail the vertical line test. This is not a function. The next one is a line with a slope. Okay, so it looks something like this. All lines that have a slope, like a diagonal line, are functions. Now, the reason I say that is because obviously there's one line that isn't a function, and that would be any vertical line. Okay, so those are not functions, but all other lines are functions. Now, this last one is interesting, and it's a bit hard. So I wanted to do it as an example, but basically I want to see if there are, if there's only one x value or only one y value for each x value. So basically I can prove to you that this is not a function by giving you a counterexample. So let's try subbing in a point, any point really, for x, and let's see how many y values we get when we sub that in. So if I put in 1 for x, and I bring that 1 over to the other side, well, I can see that there are actually 2 answers for this, right? So that means that when x is 1, it's associated with 10, and it's also associated with -10. So this is not a function, and I won't be giving you like many like this. I think it's just a nice way to hammer home the point that for every x value, you need to have just one y value. And if you can find more than one, it's like failing the vertical line test. So I'm going to stop talking now, and I would like you guys to try these questions. I actually wanted to change this one a bit. So we're going to make this a radius of 4, and we're going to move the center to 5, -2. All right. So good luck with these guys. Pause the video, try them yourself, and then look at my, resume the video and look at my answers. Good luck.